Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1000. Sorry, I'm coming directly out of another meeting. I'm a little bit scatterbrained at the moment. Had a lot of stuff going on, but hopefully you guys are doing well. Hopefully you had a good week and everything is going okay. Let me just set everything up here, share my screen. This is section R3, yes, and make sure that I can see the chat. Okay, and we are good. Again, I'd appreciate it if you can turn your cameras on and just in general participate. Let this not feel like I'm talking to myself or everyone's just so isolated. Make things feel a little bit more personal. I would greatly appreciate it if possible. Okay, all right, so let's actually jump into it. So as usual, we are having just a general Q&A type class today. And we have some public service announcements just to make sure that everyone's on the same page and we're all planning for stuff. So on Monday, we have our 5th quiz. It is the second to last quiz. Remember, we have 6 throughout the semester. So on Monday is our 5th quiz. It'll cover lectures 17 through 20. Lecture 20, you should be covering today at some point. And yeah, we're in the part, oh, some more people are coming in. We're in the part of the class now where it seems like we're just going to be rattling through topics. And so on one hand, if you're not careful, you'll be like your head is spinning. Oh, we're going through so many different things now. But on the other hand, as I was mentioning, if you really went through chapter 1 very slowly and you fully understand it, then the new topics shouldn't be too bad. Because we're still learning, we're still doing the same sort of procedures, the same sort of calculations, the same sort of concepts still apply. We're just applying them to some new things that we're introducing, so some new types of functions. So for example, during these lectures, I would have introduced the exponential and logarithmic functions. And towards the end of these lectures, I also started introducing trig functions. So again, if you know about functions in general, it's very helpful towards that. I'm just in showing you different types of functions. And so that shouldn't be too bad. So yeah, we have a quiz on Monday. Our last quiz is the 6th, and that's on November 30th. So the end of November is going to be the last quiz. The last in-class test will be on December 3rd. And then you have a final after that. So remember, the test is not going to be cumulative, unless, of course, where it's incidental, of course. Like you're going to need to know how to solve equations, even though the quiz won't specifically be on equations, for example. So the test, not cumulative, it'll cover everything that we have done since the first test, okay? So yeah, so those are the dates. So the quiz 5 on Monday, quiz 6 on November 30th, test 2 on December 3rd, and the final, I didn't put the final here because my two pre-calc classes have finals at different times and I didn't want to make a mistake. But I did send you guys the link to the final schedule. So make sure, if you haven't already, really sit down, take 10 minutes, map out when all your finals are, because you'll start to need to do some planning. In that regard, the other thing I wanted to remind you about is the Doodle Poll. I sent out a new one. This is regarding meeting on not Friday tomorrow, but next week Friday. So tomorrow we are meeting, and I think I'll send out a mass email about the time. That's to continue the study hall situation. So originally I had in mind to do like one of these guys because it's, my weeks are crazy as well. But I realized the last time didn't go according to plan. Not that it was bad or anything, but I realized I couldn't fit everything into a 2-hour window. Like I'm literally teaching a lot of people to undo years of bad habits and just kind of be a different kind of student overall. Sometimes that takes longer than 2 hours to explain. So the last study hall was very theoretical, very general plan. I put in some examples when I could, but at the end of the day, it was still very theoretical. And I've realized that there are issues with that. I realized that over time, a lot of times I give students advice and they don't really know how to follow the advice. And so they think they're following my advice when they don't, as well as, of course, you just know this from being a human being. In general, people know how to do better, but they actually don't. Everyone knows they should exercise more and eat better. And everyone kind of knows. If you were to ask them, what should you be fixing in your life? Everyone would kind of know what it is. And so, yeah, I really should study more. I really should exercise more, but very few people actually do it. The gap between knowing what to do and actually applying that are different. So I figured I would do a couple more study halls where that's sort of the focus. Going from this theoretical thing of, yeah, you should be doing this, to more of, here's how you'd actually apply it. So I think it would be useful for you guys to attend that. So we'll have one of those sessions tomorrow. We'll also have another one the following Friday. And that other one, I would really like way more participation from you guys. So hopefully when I went through the first study hall, you guys, if you didn't attend it, you can watch it. I added it to the lecture series for the class. And I actually encourage you to sooner rather than later start to try to put some things that I've mentioned into practice. The worse you're doing in the class, the more things you should try to put into practice. And then we can troubleshoot. You just let me know, hey, I tried doing what you said, Jhevon, but it didn't work out. I still did bad on the quiz. I still suck at the homework. I still blah, blah, blah. Just whatever problems you have in trying to do what I say, you should let me know what those things are before the following Friday, because I will, go into troubleshooting issues. At least that's the plan, what I'm envisioning for the last study hall. So I would need some feedback from you guys, what you guys are experiencing to actually help you with that. Yeah, I think that's it in terms of schedules. Any questions moving forward in terms of logistics, timing, how everything's going to work? Are we all kind of on the same page with like how the semester is going to progress? Any questions on that? General questions I can take right now. We're good. Questions, concerns, issues? No, we're fine. Okay. All right. Let's keep going. So I do want to tell you about what your quiz on Monday will entail, as well as maybe we can talk about. The study halls are not mandatory, so they're outside of extra classes. So someone asked if they were mandatory. They are highly, highly, highly recommended though. So even if you can't attend while it's going on, I highly, highly, highly recommend that you watch them, and that you, even more important than that, is to just actually put some of the things I mentioned into practice. Because as I mentioned, I've been teaching for a long time, over a decade at this point, and I've just noticed a lot of issues that have cropped up, and a lot of these issues have been cropping up more often and with more intensity later on. And there are many reasons for this. I think just how we've technologically advanced has a lot to do with it. The kind of things that would keep your attention now wouldn't be the kinds of things that would keep someone's attention 5-10 years ago. A lot of people have a lot of shorter attention spans, and there are just a lot of things where just the lifestyle today makes studying a little bit harder and a little bit more fuzzy and a little bit more, students just don't really know how to do it very well anymore because of just how everything is. So it's highly recommended, even though it's not mandatory. I do think everyone can benefit from it. Even the students who are doing well in the class so far, I think should still attend, because you're going to hit something hard in life eventually, right? You're going to have right? A lot of you, this is like your first semester. I mean, you have 4 more years to go. In that time, you're going to come up to a challenge and you're going to want to know how to deal with it. So one of the things that are also an issue is people just not knowing how to deal with challenges. So yeah, I think everyone stands to benefit from this. Okay, all right, that being said, let's actually jump into the quiz material. So I think I got all the sections here, right? So the quiz, and I'm talking about the quiz on Monday, covers lectures 17 through 20. If you want to break this down by section, it covers parts of section 2.2, namely piecewise functions, 2.6, 2.8, 3.3, 4.1, 4.2, 4.3, 4.4. So those are the sections. So almost all of chapter 4. I think there are 2 sections of chapter 4 that we are covering that are not covered on this quiz. Okay, so sort of the essential topics, the things I would expect you guys to know a lot about. There are going to be about 9 of them for this quiz. So piecewise functions is one of them. We already had a bonus problem or even a couple bonus problems on that in previous quizzes already. Transformations of functions. This is talking about like shifting. Do you know what would happen if you add a number to a function? So if I take f of x plus 5, what happens? If I replace all the x's in f of x with x minus 5, what happens, right? How do you shift left and right? How do you stretch? How do you shrink? So just when you actually do arithmetic operations on the formula for a function, do you understand what happens to the graph? Do you understand what this means for the function in general? So that's what transformations of functions is referring to. Inverse functions, a very important topic. I just want you to know about inverse functions, what they are, what are their properties, how would you graph an inverse function, how would you find the formula for an inverse function if I gave you a formula for the original function. If I gave you 2 formulas for functions and I ask you, are these functions inverses of each other? I expect you to know how to check whether or not that is true. So that is what you need to know about inverse functions. We also learned that for a function to be invertible, meaning that if I give you f of x, how do you know that there exists an inverse function? The functions have to be one-to-one and onto. These have very different meanings. One-to-one just means it passes the horizontal line test as well as the vertical line test. So all functions have to pass the vertical line test. But one-to-one functions will also pass a horizontal line test. So if you draw any horizontal line, it will only touch them at one point at most. So basically one-to-one just means each unique x value will have a unique y value. So a function just means that each x value should be mapped to one y value, but there's no restriction on reusing the y value. So you can have multiple x's attaching to the same y value, and that's fine for a function in general. However, if once an x value attaches to a y value, no other x value can attach to that particular y value, we call such a function a one-to-one function. And it's actually very important for inverse functions to know that that is true. Also, onto, meaning this is basically when the codomain is equal to the range, meaning the set of possible outputs happens to be the entire second set that you're mapping into. So that's what functions called onto or surjective in that case. So you need to know how to check for that or how to recognize these guys from graphs, right? So if I graph a one-to-one function, can you tell me that it's one-to-one? Would you be able to not tell me that it's one-to-one? If I graph an onto function, would you be able to tell me that it's onto versus not onto? So yeah, a lot of graphs and pictorial things there as well. Is a few computations. When it comes to long division of polynomials, that's another topic. A lot of you might have learned another technique here, synthetic division. So long division slash synthetic division. So some of you might have learned that. I did not cover this in class. Synthetic division, not covered in class. But you can use it when appropriate. So if you learn synthetic division and you want to do it, it's fine. Just do try to understand long division because I am going to ask you questions specifically on long division as well. And if you learn the synthetic division, there are little nuances to that. So you should, if you really like synthetic division and you want to do it, just make sure that from your synthetic division work, you can actually match up each step to a particular step in the long division. So at least make sure you know that, as well as knowing when synthetic division is appropriate. So personally, I don't really jive with synthetic division, to be honest. But as you guys know, I show you guys methods even when I don't particularly use them and I don't particularly like them. The reason why I chose against this for synthetic division is there are actually cases where synthetic division does not work. And so it's not true that you can literally apply synthetic division in all cases where you can apply long division. And because it was so limited, I just decided not to talk about it at all. Like I wouldn't want to show you a method where it only works some of the time, and then now you're confused which method to choose from when. So yeah. So synthetic division works very well when you're dividing by a linear factor, but if you're not, so like if I give you one polynomial divided by a quadratic, synthetic division suddenly doesn't work anymore, right? So that's kind of why I don't like it. So synthetic division only works when you're dividing by some sort of linear function. So something like that looks like ax plus b. So if you're dividing a polynomial by 2x plus 3 or 5x plus 11 or x plus 1 or something like that, synthetic division will work. If you're, and by the way, if the coefficient of the x is not 1, you have to tweak it as well. So if you want to say divide one polynomial by 2x plus 3, then what you want to do is you want to actually divide out the 2 first. So you would think of it as dividing by x plus 3 over 2. And then you just, whatever answer you get, you just have to remember to divide by a half. So there are a lot of little nuances with synthetic division. It just, to me, it's overly complicated. The most straightforward way to use synthetic division is if you're dividing by x plus a number. In every other situation, you have to tweak it too much. And some situations, it just won't work at all. So I just decided, let's not even go there. So I don't particularly like it, but there are many other reasons why I just decided not to even talk about it at all. However, if you love synthetic division and you do it and you show your work for that and it's correct, you use it in the correct situation, you do the correct work, I'll still give you credit for it. It's not recommended. I far recommend long division as taught in class over synthetic division. So I thought I would mention that. Not covered in class, but you can use it when appropriate. Note, it does not work in many cases. Note, it does not work in many cases. Specifically, it works well if dividing by something like x plus a constant. Needs to be modified if dividing by something like ax plus b where a is not 1 and does not work otherwise. Okay, so just be aware of that. Like if you're going to use synthetic division, like I said, it's not going to be wrong. And if you use it in the right situation, in the right way, I'll give you full credit. don't let that be. I'm not one of those guys like, it's my way or the highway, right? So there are a few times when I might ask you to, do I ever actually ask you that in pre-calc? I know in like my calculus class, there are times when I force students to use a certain method. In general, I don't though. But yeah, for the most part, I don't force people to use my way. I have very good reasons whenever I recommend a certain method, but in general, you don't have to do it by my method if you don't want to. Yeah, but just be aware of all the pitfalls of using other methods. The sixth topic would be to use the rational roots theorem. Spoke about that in class, and especially using it to help you factor other polynomials. So this is like when I ask you to factor a polynomial. So we end up in this situation. So before, we know very well about how to factor polynomials. We know the AC method. We know the trial and error method for quadratics. We know, oh, factor out the GCF. If it has 4 terms, try factor by grouping, etc. We know all of that. But then there are times when you would have a polynomial where the techniques that I've shown you so far just don't seem to work. They don't seem to apply. And the rational roots theorem provides another way of actually figuring out what those guys are to factor. So I mentioned what the rational roots theorem is and how to apply it. And we do examples where I help you factor those. So the rational roots theorem is very important. So I might ask you to factor this random polynomial, and I don't even tell you anything about how it's factored, but you should be able to figure out how to factor it based on the rational roots theorem. This is something that is very useful. I am also teaching Calculus 2 this semester, and there are times when this came up in my Calculus 2 class, and a lot of students struggled because of it, because they don't remember this. So it's very important, it's very applicable, you will use it for a long time. So, and that's true. I mean, it's pre-calc, that's true for everything else. Like everything I teach you guys here, you'll see a lot of Calc 1 students, a lot of Calc 2 students, a lot of Calc 3 students making mistakes based on this stuff. It just goes to show you, like I said, a lot of times people get things wrong for the very basic foundational reasons. When you really understand the simple, it makes understanding the more difficult a lot easier. And it's one of the reasons why I spent so long on chapter 1, because it was really, really important for you guys to understand the very basics. And hopefully you guys paid attention to that and didn't just gloss over, oh, I know this already. I'm not kind of half paying attention. That is a mistake. Pay a lot of attention, especially to the basics. Exponential functions and the natural exponential function. So the natural exponential function, I am specifically talking about a function that looks like y equals e to the x. But exponential functions is like a to the x, where a is a non-zero constant. In general. And I think in class, I only dealt with the positive ones, because there are issues when you have a negative constant as the base that I didn't want to get into, including things like complex numbers can come into play and a lot of stuff. So we only had bases that were positive, but those are the exponential functions. The natural exponential is when we use base e, and I spoke about what the number e is, Euler's number, and how it came about, what it means, etc. But it is the most important exponential function in calculus. It's the most important function in calculus, period. And there are actually a lot of math people, I would say, who think y equals e to the x is the most important function in all of mathematics. It's a very, very important function, very unique function, and very useful function. In fact. Then I looked at logarithms. So went over logarithms, what a logarithm is. This is pretty much looking at exponential functions from another point of view. When you want to solve for the power, the logarithm is the power. I explained that definition. I went through the log rules. There are about 10 of them, which are very, very important for you to know. There are 5 of them where it's mandatory for you to know. And there are another 5 where it will really be nice for you to know them. I highly recommend that you know them. And probably if you do a lot of problems, you'll end up memorizing them anyway. But it'll make your life easier, a lot easier if you just know them right off the bat. Things like knowing the log of 1 is 0, right? Technically, you could prove that from the definition or anything that I've said before, but just knowing that right off the bat, the log of 1 is 0 is just, it's something that comes in handy so often, it's not even funny. Just knowing right off the bat that the log of 0 does not exist, it's undefined. Log of any negative number does not exist, undefined. So just knowing some of these things right off the top of your head can be a great help. Okay, so we talk about logarithms. We also talk about log functions. We talk about the fact that a log function is the inverse of the corresponding exponential function. So the log function with base a is the inverse of the exponential function a to the x, right? So y equals log to the base a of x is the inverse of the function y equals a to the x. And that's actually pretty useful in the next section, meaning where we talk about the bonus and now I'm kind of going into bonus territory because it wasn't covered yet. In the next section, we're going to learn to solve equations with exponentials and logarithms, and knowing the inverse is very important to that. As you probably recognized when we went through equations, knowing about inverse operations was very important, right? So if I want to solve an equation and there's something being added to both sides that I don't want, I have to do the inverse operation. I have to subtract from both sides. Or there's something multiplying that I don't want, I have to do the inverse, divide both sides by that thing. In the same way, when you have a log in something and you want to get rid of it, you're going to use exponentials to get rid of it. Whenever you have an exponential that you want to get rid of, you're going to use logs to get rid of it. The log and the exponential perform inverse operations. So you can use one to cancel the other, quote unquote. So that's very important. So I'm not going to ask you to demonstrate that in the quiz on Monday, but it is something that you should know, and it's something that you will have to demonstrate you can actually apply to an equation in the next quiz, in the quiz 6. Okay, so logarithms and log functions, very, very important. And there's so many things. I'm not teaching Calc 1 1206 next semester, as far as I know. But there are a lot of things, those of you who need to go to the next class, Calculus 1, the 1206 version, I prove a lot of the rules in calculus using exponentials and logarithms. So they're very important. They're the building blocks of a lot of important concepts in calculus. Okay, if you're going into 1203, usually I don't prove stuff in that class, and I don't think anyone else does. That's more like applied calculus. It's sort of a watered down version for, depending on your major, you can do that one. Then the last thing is to simplify exponential and log expressions. So I can give you some convoluted expression with logarithms, and I can ask you to simplify the expression by like expanding it into smaller logarithms. Or I can give you a bunch of small logarithms being added together, and I want you to combine it into a big logarithm. Or I can give you an exponential with a complicated power, and I expect you to simplify it, write it down as a simpler power. And yeah, things of that sort. So simplifying exponentials and logarithms. So those are all the topics that were covered in lectures 17 through 20. So it sounds like a lot, but at the end of the day, we're using operations that we know how to deal with. We know how to raise things, like we know how to divide, we know how to multiply stuff, we know how to sketch graphs right now, we know how functions work. And so we're just applying all these old ideas to just some new, I guess, and these are the two new functions, the types of functions that we learned about, exponentials and logarithms. In this class, there's one more type of function I'm going to introduce, which is the trig functions, which comes after. And so at this point, you'll probably, if you're keeping counts, you'll notice that there are really 6 kind of basic functions that we like. Polynomials, rational functions, radical functions, exponential functions, logarithm functions, and trig functions is the 6th one. And it turns out that these guys are known as the elementary functions. These are the same functions you will be using throughout your calculus career. Calc 1, Calc 2, Calc 3, you're not really going to learn about any new types of functions, at least not in any great detail. And any function that you encounter in those classes will be a combination of all of these functions. These 6 functions are like the 6 infinity stones. You can actually build everything up. All of elementary mathematics is built up of these guys. And yeah, you're not going to learn about any crazy new functions after that. And you're going to realize that these guys provide a very important foundation. There will be other kinds of functions, but there will be in much more complicated contexts in classes much higher than a regular calculus class. Okay, so those are the topics. Now, if you wanted to go ahead and be prepared for the bonus, I mentioned here what I can ask for the bonus. So actually solving exponential and log equations, graphing exponential and log equations. So if I give you the equation of an exponential or a logarithm, you should know how to sketch it, know how to find where the asymptotes are, all of that, do a very detailed sketch. And then I go into talking about angles and trigonometry. So the lecture after, so lecture 21 is where I go through solving exponential and log equation and drawing log graphs and all that stuff. This spills over into lecture 22, and in lecture 22, I start talking about trig functions. So if you want to talk about the bonus for any of those will be the guys. So I'll have lecture bonus material on the quiz from like lectures 21 and 22, maybe 23. I don't know. But also, as you should probably guess, we're getting very close to the end. So I think there are 25 lectures in total. So we're very close to the end. We're already on lecture 20 right now. So there are really 5 lectures, and that'll be all she wrote. So things are really wrapping up. So again, I highly encourage you to go over the schedules for everything, start putting things on your calendar, knowing when things are, and start your planning based on that. Putting some of the tips I gave in study hall and the tips I've been giving you throughout the class on how to actually apply yourself, how to get things structured, how to move on, and so forth. And now we're going to sort of move to the Q&A section. So if there's anything about these topics that when you were going through it, you didn't understand or you weren't sure, or you want to know maybe what are the kinds of things I would ask or something like that, at this point, I'll open the floor if anyone wants to ask about that. Maybe you're trying some homework and it wasn't going well or anything. I highly encourage you to actually engage at this point and let me know. And yeah, so give you guys a few seconds to compose your thoughts there and maybe ask some questions about anything here.
I actually have a question from the homework that was giving me trouble.
Sure.
It's a long division one.
Okay, awesome. Okay, Charlotte. Yeah.
So
do you have the particular question?
Mm-hmm. It is p of x equals x cubed plus 9x squared minus 5x plus 5. And then it's d of x equals x minus 4.
D of x equals x minus 4. Okay.
Yes. And then they were asking to write it, express p in the form of p of x equals d of x times q of x plus r of x.
In the form p of x equals, come again, d of x, q of x
plus r of x.
Plus r of x. Right. So this comes from the long division. Remember when you're doing long division, how that would work out is the idea here is you're going to take the p and you're going to divide by the d, right? And that's going to lead you to sort of this long division setup here, where the d is going to be the guy on the outside, the p would be the guy on the inside, the q is the guy that shows up here. They call it q because it stands for quotient. And the p here, the d here, they call it d because it stands for the divisor. And when you go through the process, and you start doing blah, 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 doing that long division, if you have something that's left over here, this is the remainder is going to end up down here. And this is what's left over after you can divide everything. Okay, so in terms of how these guys will all relate to each other, that is how it would work. So that's how you would find all these forms. So this actually comes from, they labeled everything very suggestively here. And so, yeah, D is really means divisor, Q means quotient, R means remainder. So it's very suggestive of where the positions of each of these things would actually show up. So that's the first kind of concept I would say you should know. So yeah, your P, your guy down here is actually going to be this times that plus the remainder. So that's just overall how these guys all fit together. And that's sort of the general concept and how it sort of relates to long division. So that being said, once you kind of know that, you would know that what the question is actually asking you is to just divide the P by the D, and then you're just going to write out this based on what happens, okay? So first of all, did you realize that that's what you were supposed to do?
Yes, but I kept getting it wrong, so I kept redoing it, and each time I would
Okay.
get a different
All right.
Q of X. So I wasn't sure if it was
All right, so good. So there are two parts to any problem. First, you have to know the general strategy and the general concept, and you think you're okay with that. So now is the actual execution, right? So it's one thing to actually say, I know in theory how to do this problem. It's another thing to actually pull it off. So it looks like you're having trouble with the pulling it off part. So let's actually do that. So what we would do here is the D is X minus 4. And the P is X cubed, 9X squared. Like that. And now remember, the first setup is make sure you have a placeholder for all powers of X 3 to 0. So that's very important. So for example, if they did not give me, if there was no 5x here, so they just told me it was x cubed plus 9x squared plus 5, I would artificially put in a 0x, right? So you want to make sure that you have a place for everything. So that's the first thing, right? Things have to line up correctly. Otherwise, you can get confused from that. It's very important that you line things up correctly, both in the long division method and the synthetic division method. So that's the first thing. Make sure everything is lined up underneath the bar. So these are just some troubleshooting tips. Sometimes students will get things wrong because of reasons like that. They just didn't line things up correctly. So make sure that things are lined up correctly. Okay, so that's the first thing. So understand the general concept of how these guys fit together. Understand how things need to be lined up when you actually start computing the problem. Okay, right. So now all the powers were accounted for. We have power 3, power 2, power 1, power 0, right? So the 5 is 5x to the 0. Right. So maybe tell me how you went through this.
So the first thing I did was I said like what do I have to get x cubed from x? So it was x squared.
Right. So you take the x, you divide into x cubed.
Mm-hmm.
Right? Okay. And that would give you x squared. Right?
Yeah. Mm-hmm.
And then what did you do?
So then I multiplied the x squared by x.
Right, so you actually multiply it by both of these.
Mm-hmm.
And then you write that below. And again, you make sure everyone lines up. So you take x squared times x, you get an x cubed. So I line that up under the x cubed. You take x squared times minus 4, you get minus 4x squared. Make sure that lines up under the 9x squared. Then what you're going to do, you're going to subtract this line from the line above. So x cubed subtract x cubed, so that's gone. Then you're going to have a 9x squared minus a minus 4x squared, which gives you 13x squared. Are we okay so far?
Yes.
Okay, and now what?
So now you divide x into 13x squared, and
Right,
then
you repeat this process exactly, right? You just keep going over and over this. Okay, so once you understand what I just did, does anyone have a question on what I just did? Okay, so once you understand what I just did, you now just literally rinse and repeat. So you take the x divided into the 13x squared. You're of course going to get plus 13x. Line that up over the x. Then I'm going to take that 13x, I'm going to multiply everybody there. So 13x times x gives me the 13x squared. 13x times minus 4 would give me what?
52.
Minus 52x. And I'm going to subtract that. So this minus 5x, I'm going to actually combine with that. So the 13x squares, they die. And then I'm going to have minus 5x plus 52x, right? Because it's minus a minus 52. So what would that give me here?
Oh, 47x.
47x. Repeat the process. X into 47x, you would have plus 47. You take the 47, you multiply by the x. Then you take the 47, you multiply by the minus 4. And what's that? 47 times minus 4.
Uh, 188.
Okay, you want to double check that. So, I mean, in the quizzes, I'll give you guys smaller numbers, of course, because I don't, I'm not testing you on your arithmetic abilities. I'm testing you whether you know the thing. So for the homework, though, you do want to make sure that you're not making any mistakes here. So 188, I agree. So now you have plus 5 plus 188, right? So that would give you what, 193. Agreed? So yeah, and so now because we know the concept from earlier, I know that this guy here on top of here, that's my Q. This guy here is my R of X. And so this means my P of X, which is X cubed plus 9X squared minus 5X plus 5, I can actually write that as the Q times the D. So it's going to be X minus 4 times the guy that I had up here, X squared plus 13X plus 47. And then I add separately the remainder. And that would actually be the answer. This also goes to show you something else we talked about when it came to factoring. It turns out that if you could factor the polynomial, what would happen here is that the remainder would be 0. And so you'd actually just be able to write this polynomial as a factored form. But here the remainder is not 0. So it turns out that this guy can't factor. At least it can't factor using an x minus 4 as one of the factors. I don't know if it factors otherwise. Okay, any questions on that? Yeah, so long division, definitely an important topic. I'm definitely testing on long division, and you'll right. So, and chances are, if you'll need to know long division for future classes, and if you are in one of my Calc 1 or Calc 2 classes in the future, you would definitely have problems where you're going to need to actually remember how to do this. So yeah, long division. Probably one of the more technical topics of the ones that are covered in these guys. So definitely something you want to make sure that you understand. Any other questions from homework or just in general from these topics?
In lecture 17, when you were doing the computing inverses.
Yes.
So if we're given an equation and we find the inverse of it, do we have to find the inverse of that to show that they're both inverses, or do we only have to do it once?
So, I mean, if I ask you to find an inverse, I probably won't ask you to prove that it's the inverse at the same time. So so both of these would be different questions. I wouldn't really ask these at the same time. So let's actually take those one by one. So let's talk about finding inverses versus proving two given functions are inverses of each other. So let's actually talk about finding inverses. So if you're given an invertible function, f of x, to find f inverse of x, the process is the following. You would set y equals f of x. The second thing is you'd switch x and y. So you would get x equals f of y at this point. And then 3, you would solve for y. So this would be an equation, and we now know how to solve equations. You would solve for y. So then 4, you would get y equals some other function. And so you can now say the inverse function is that other function. Okay, so that would be the procedure. And after that, you won't have to find the inverse of that to show that you get the other one. This would be the end, right? So example, if I said f of x is equal to x plus 2 over x minus 1, find f inverse. So that could be a problem. Which of the following is the inverse of f? So what you would do is you would set y equals x plus 2 over x minus 1. You would switch x and y. So now you'd have x is equal to y plus 2 over y minus 1. And now you try to solve for y. And so you can, do the cross multiplying. This means that xy minus x is equal to y plus 2 by just like multiplying that. And yeah, now you want to solve for y. So you want to isolate all the y's on one side. So I would say bring this y to that side and bring that x to the other side. Factor out a common y. And then you would actually divide. And so this would be your F inverse. And you'll notice this is actually the same as the original. This is not true in general. I just made an example off the top of my head. So it's possible for a function to be its own inverse, but this is the same as f of x. This is not true in general. F inverse can be different. I just happened to pick some numbers that didn't work well.
I have a quick question about
Yes.
this. Could you be doing a problem like solving an inverse problem and it doesn't like work out and that's how you know it doesn't have an inverse? Would that be like your like signifying thing? Or like what would be an instance where you're like solving a problem and then like there's no inverse?
Oh, you would, so that would be something that I could ask you in the beginning. Does it have an inverse? The best way to answer that is to check if the function is one-to-one and onto. That would be the best way. Now, it is true that if it doesn't have an inverse, you will not be able to do this. But the risk there is the following. It's possible that you can solve the equation, but you just don't know how to, right? So just because you can't actually solve this doesn't mean that there's no way to actually solve it. You know what I mean? So it depends. If you're sure that I definitely know how to solve this equation and I know for sure it's impossible to actually solve for the y, then yes, you can actually use that to say it has no inverse. The only issue with that is that method is only as good as your blind spot. So if it's possible that you could have solved for y, but you just didn't see it, you could end up making a wrong conclusion.
And let's say, for example, like this problem, how, like, I know on a graph, like how to see one-to-one, but like how with like this function, like how would you see if it's one-to-one? Would you just have to like graph it?
No. So on the graph, yeah, you can identify one-to-one by actually, I think I want to deal with that after. Okay, so let me put that in chat. Identify one-to-one. Because let me finish this topic first and I'll come back to that question, right? Because
Right,
there were two things we wanted to do, finding inverse and proving that two functions are inverses of each other. Let me just make sure that we know how to do that. So that would be that. Now, when it comes to proving functions are inverses of each other, so this is, say, given f of x and g of x, you can determine if these are inverses of each other by two things. You would find f of g of x and g of f of x, which means you plug one function into the other. And two, based on the result, you will know what the answer is. If f of g of x equals x, and both of these have to be true, and g of f of x equals x, then they are inverses of each other. Otherwise, they are not. So going off the above, which I don't know, maybe I should do another example, one that isn't the same. I think if I made the coefficients the same, if I made the coefficients of the x's different, I'll get a different answer. So let me do another example. So f of x equals, say, 2x plus 1 over 1 minus x. Find f inverse. So let's actually just go through that process again. And I think the answer will be different this time. So y equals 2x plus 1 over 1 minus x. For inverse, I'm going to switch x and y. And then solve for y. So this means that x minus xy is equal to 2y plus 1. Let me move the 1 on this side and the xy on that side. So this means that x minus 1 equals y times x plus 2. And so this means that y is x minus 1 over x plus 2. And so the inverse would be x minus 1 over x plus 2. Right? So that's a different from the one above. Now, a separate question could be, so let me just verify that. I won't ask you to do both of these at once. A separate could be determine whether f of x equals the first one, 2x plus 1 over 1 minus x. And g of x, the guy I just found. So we know that this should, the answer should be yes to this. X minus 1 over x plus 2 are inverses of each other. Okay, and in this case, you would just jump in and start plugging one into the other. So you'd say f of g of x. Well, what is that? That just means you go to f, and everywhere you see an x, you plug in g of x. So that's 2 times x minus 1 over x plus 2 plus 1 over 1 minus x minus 1 over x plus 2. And so this would be, well, 2x minus 2 over x plus 2 plus 1. And this will be 1 minus x minus 1 over x plus 2. This is a compound fraction. I know the quickest way to simplify that is to multiply and divide by the LCD. So that's what I'm going to do. Multiply this, multiply that, and multiply this, multiply that. So in the top, The x plus 2's cancel, so I'm left with 2x minus 2, plus here I have x plus 2, over the bottom x plus 2 times 1 is just x plus 2. And here the x plus 2's would cancel, I'd be left with x minus 1. So now you'd realize here I have 2 minus 2, so that goes away. And I would have 2x plus x. So that's 3x on top. On the bottom, I would have, well, x minus x, so the x's go away. And then I would have a 2 minus a minus 1, which gives me a positive 3. And those cancel. And so we get x. Then I would go and I would find g of f of x. Right, so I get x in the first one, which is good, but I have to make sure I get x in the second one. So g, this is f of x minus 1 over f of x plus 2. And my f of x was 2x plus 1 over 1 minus x. Again, multiply by 1 minus x, 1 minus x. To simplify, that would give me 2x plus 1 plus 1 minus x. And I would have 2x plus 1 plus 2 minus 2x. And here I would have, well, 2x minus x is just x, and then I have a plus 2. And then if I multiply this here, I would get 2x plus 1 plus 2 minus 2x. So then, wait, something's not working. Oh, it's a minus 1 here. Okay. Yeah. So you only get x on top. And then I would have that. And was that supposed to be a plus 2? Okay. So 2x plus 1 plus 2 minus 2x. There's still something off here. Because I should get a 1 in the denominator. Did I copy these down correctly? 2x plus 1 over 1 minus x. Minus 1 on top and a plus 2 on the bottom. Oh, because I messed up the sign before, so I missed the sign would actually affect that. Okay, so on top here now I would have 3x. Right, and on the bottom I would have 3. So I get x again. So now I can say since f of g of x equals x and g of f of x equals x, f and g are inverses of each other. Right, so I did two. I wouldn't ask you to do both of these in one problem, but it's because both of these were problems that were raised, questions that were raised. So if I give you a function and ask you to find the inverse, just assume it exists and go through this process. If I give you two functions and then ask you, are they inverses of each other? Then you go through this process. there's only one way that they are inverses of each other, and it's if both composite functions give you x as the result. If one of these give you x and this gives you something else, or they both give you something else, then they are not inverses of each other. So they both have to output x for you to know that they're inverses of each other. It's possible that you can plug one into the other and get x, but when you do it the opposite way, you don't. So that's very important. And sometimes that also depends on the domain of the functions and all sorts of things. So if you have like a radical here, that might be important. You need to know that, oh, well, technically I can't plug in negative x's, so blah, blah, blah. Yeah, but that's just as a general principle how you would go about answering these two types of questions. Now, let's say to answer the question above, how to determine if a function f of x is 1 to 1 or onto. So let's talk about 1 to 1. So there are two situations that you should know. Well, for one, there's the graphically. And this means passes, it's a function that passes horizontal line test. Right, so it has to be a function first, which means it already passes the vertical line test. So it's 1 to 1 if it also passes the horizontal line test. So if I were to give you examples of two functions, something like that. Versus something like this. Then here, notice that no matter where I draw a horizontal line, it'll touch the function at most one place. Whereas here, if I draw a horizontal line, it can actually strike the function in 3 different spots. So this here is 1 to 1 or 1-1 or injective. These are all different names for the same thing. This here is not 1 to 1. Yeah, so that's how you tell from the graph. By formula, you need to show that, say, f of A equals f of B implies that A must be equal to B. So if the outputs are the same, then the inputs must be the same. So for example, and these are just some silly examples, probably the same ones I gave in class as well. So I could give you the function x squared on negative infinity to infinity. And I can ask you, is this 1 to 1? So what you would do is you would set f of A equals f of B. So this means that A squared equals B squared. You just plug them in. Or let's even just do +1, just to make it a little less trivial. So I'd have A squared plus 1 equals B squared plus 1. So now I want to simplify this equation. I can subtract 1 on both sides. And so I would get A squared must be equal to B squared. And now to actually solve this, I would take the square root of both sides. but we do know that when we do that, we get a plus or minus, and that is a problem. So for instance, you'll notice that f of -1 is equal to f of 1, right? Because if I take -1 squared plus 1, it's the same as 1 squared plus 1. These would both be equal to 2, but clearly -1 is not equal to 1. So you have the first equation is true, but the second one wasn't. So that would be how you'd recognize by a formula. Or you can even just, you can show something is not one-to-one by just doing this. Pick two numbers and show that when I plug them in, I get the same output, but I can get the same output from different inputs. So it's sort of like when you're doing something here, right? So there was an output that gave you this y value, but there's another output that gives you the same y value, right? So both of these map to y1, even though they're different x values. You don't want that. So you just want to use a formula to show that that is true. Conversely, so here, so this would mean f is not one-to-one. Now you can notice here that if I were to restrict this so I don't count the negative numbers, if I only went from 0 to infinity, it turns out that this would be one-to-one because the minus wouldn't apply, right? So for example, another example, let's say I had now f of x equals x cubed minus 7. Then notice that if I here set f of a equals to f of b, this means that my a cubed minus 7 equals my b cubed minus 7. This means that I can actually subtract things from both sides. So this means that a cubed equals b cubed. And at this point, I can take the cube root of both sides. And that will give me a equals b. Now remember, the cube root maintains the sign. So if you're a negative underneath, it keeps the negative. If you're a positive underneath, it keeps the positive. So you'll either have both positives on both sides or both negatives on both sides. In either way, both sides will be the same. Your a will be equal to b. They'll have the same sign. And so you can say here, f is one-to-one. Now here, yes, I could actually just graph x cubed minus 7 because I know about transformations of functions. It's just the graph of x cubed shifted down, and I can graphically see that it passes the horizontal line test. But this also works for more complicated formulas that you wouldn't want to have to graph. Yeah. And this would also work with something like, maybe I can do a little more complicated example. Maybe one of the guys we had up here. 2x plus 1 over 1 minus x. So it's not completely trivial. We know that that's one-to-one because it has an inverse. We found it. So let's actually prove that it is one-to-one. So here I would set f of a equals f of b. This would mean 2a plus 1 over 1 minus a is equal to 2b plus 1 over 1 minus b. Now I want to see if, assuming that equation is true, is it necessarily true that a must equal to b? Well, we can cross multiply. And I would get 2a plus 1 times 1 minus b equals 2b plus 1 times 1 minus a. Expand, this is 2a minus 2ab plus 1 minus b. Expand this is 2b minus 2ab plus 1 minus a. I can subtract the 2ab from both sides. I can subtract the 1 from both sides. And I can move this a over there. And I can move this b over there. this would mean that 3a is equal to 3b. And then I can divide both sides by 3. And look at that. A must be equal to b here. So f is 1 to 1. So as a formula, if you don't want to have to graph it, because you probably wouldn't want to have to graph something like this, you can actually just do it based strictly on the formulas. So hopefully that answers your question. In terms of onto, it just means that the entire range is equal to the codomain. So for onto, given a function from A to B, where of course A is your domain and B is your codomain, you must show for any element in B, there is some element in A such that f of x equals that element. If this is impossible, it is not onto. So silly example there. So let's say I have a function from all the real numbers to all the real numbers defined by f of x equals x squared. What I can say is this is not onto because note -1 is in R, the codomain, right? I'm referring to this R right here. But there is no X in R, the domain, such that f of x gives me -1. Right, because if I set, because that would mean that x squared is equal to -1, which we know has no real solution. So you can show that it's not onto by doing something like that. Just show that I can pick an output where there's no input. And this is also true on the graphs. Like if I tell you what the codomain is, and if you notice that there's no output for that codomain, so again, graphically, in the above, you would realize that my graph looks like this, but then I realize that there's no graph down here. So I can clearly see there's some y values where there's no graph for them, right? So it means that not all outputs are possible. So if I think of my codomain as all real numbers, clearly this picture misses all the negative ones. So there are a bunch of things in the codomain that I cannot get from my function as an output. So that's how onto works. Okay, so, and we're actually over time right now. But if there are any quick questions, I can just take it in a few minutes. I guess the rest of you are allowed to leave if you want.
Thank you.
Okay, all right, well, good luck. Keep studying, do all the homework. If you have questions, you can reach out, and see you guys next week. we will, yeah, we'll stop there. All right, have a good day, everybody. Get through those lectures, and I'll see you guys in the next one. Ciao.